All right, in this video, we're going to introduce compound inequalities. So we're going to look at solving and graphing solutions of compound inequalities. So compound inequalities involve more than one inequality. So in our last section, we looked at only solving one inequality at a time. So when you solve more than one, it's called a compound inequality, and they're going to be connected. The inequalities are going to be connected by either the word and or the word or. And in this video, we're going to take a look at compound inequalities that involve the word and. So a number is a solution to a compound inequality that involves the word and if it's a solution to both inequalities. So it has to be true for both inequalities. In other words, let's say you're told that you need to go to the store and pick up some potatoes and milk. So you're supposed to go to the store, you have to buy potatoes and you have to buy milk. So if you come back with both potatoes and milk, everything's fine. But if you come back with only one of the items or none of the items, then you screwed up, and in this case you didn't get the job done. So with compound inequalities separated by the word and, it has to be a solution to both inequalities, has to be true for both. From a visual interpretation, if you graph each individual inequality, so here we have x is greater than or equal to -1 and x is less than 2. So greater than or equal to at -1, closed circle, less than at the 2 is an open circle. If you graph each individual inequality, the solution for and is the part where they overlap. So x is greater than or equal to -1, closed circle -1, and shades forever to the right. X is less than 2, open circle at x equals 2, and shade forever to the left. So they overlap in between the two numbers. So solve and graph each. We got part A, we have -3 is less than 2x plus 1, and at the same time 2x plus 1 is less than or equal to 3. So we can actually separate these into two different inequalities. So subtracting 1 from both sides, in our first inequality we get -4 is less than 2x, and in our second inequality we get 2x is less than or equal to 2. And for the first inequality, I again like to have my variables on the left-hand side when dealing with inequalities. So I just flip the left and right sides. Make sure that the alligator still gets the 2x. When you flip both sides, you have to flip the inequality sign as well. Didn't do anything with this inequality over here. So our last step is to divide both sides by 2, and for our first inequality, we get x is greater than -2. For our second inequality, we get x is less than or equal to 1. So we set up our number line. Our first one, x is greater than -2, open circle at -2, because it is just greater than, it's not greater than or equal to, and it gets shaded forever to the right. For our second inequality, x is less than or equal to 1, I'll just shade that one below the number line. So because it's less than or equal to, it gets the closed circle at 1 and then shade forever to the left. And what we want to do is we want to find where these two parts, the red and blue shadings, overlap. And they overlap between the -2 and the 1. So open circle at -2, closed circle at 1. Any number in between here will make our original inequality true. So for instance, if we pick x equals 0, -3 is less than 0 plus 1 is 1. -3 is less than 1. And here, if x is 0, we get 1 is less than or equal to 3. That's also true. However, if we pick a number like 10, for this one, -3 is less than 21. That's true. But this one says 21 is less than or equal to 3. So that's not true. So a 10, which would be way over here, does not make this second inequality true, which means we can't shade it on the number line. So again, for the word and, they both have to be true. And if you see a compound inequality written this way, where you have a left side, a right side, and a middle, this implies the word and, where they're joined together by the expression in the middle. Part B, 1 less than or equal to 2x plus 3 less than 11. So we can separate this as 1 less than or equal to 2x plus 3, and also at the same time 2x plus 3 is less than 11. Subtracting 3 from both sides, we get -2 is less than or equal to 2x for our first inequality, and subtracting 3 from both sides, we get 2x is less than 8 for our second. And switching this around for our first one, so it's 2x on the left-hand side greater than or equal to -2. And then divide everything on both sides by 2. We get for our first inequality, x is greater than or equal to -1. For our second inequality, we get x is less than 4. So we're looking for all the values of x that are greater than or equal to -1 and also less than 4. So greater than or equal to -1, closed circle and shade to the right. For x is less than 4, open circle and shade to the left at x equals 4. And where they overlap is right here in between. So we got a closed circle at -1, open circle at 4. Any number in between -1 and 4 will make both inequalities true. All right, part C, we have 2x minus 7 greater than 3 and 5x minus 4 is less than or equal to 6. So here we're not combining them with the same inequality. Here we're using two separate equations. We have 2x minus 7 and a 5x minus 4. So if they're the same, then we can condense them. So we'll solve each one individually. We get 2x minus 7 greater than 3, 5x minus 4 less than or equal to 6. Adding 7 to both sides in our first one, we get 2x greater than 10. Adding 4 to both sides in our second, we get 5x is less than or equal to 10. Then dividing the first one, both sides by 2, we get x is greater than 5. For the second one, dividing both sides by 5, we get x is less than or equal to 2. Now, graphing each one, for x is greater than 5, open circle at 5, gets shade to the right, all numbers to the right of 5. For x is less than or equal to 2, we have closed circle at 2, shade to the left. Notice these do not overlap. So because they don't overlap, there's no number that will make both inequalities true. So for instance, even in between, if we pick a 3, 2 times 3 minus 7 is not greater than 3. And 5 times 3 minus 4 is not less than or equal to 6. So because our graphs, our shadings do not overlap, then there's no value that will make both inequalities true, which means there's no solution to this problem. So, all right, that about does it for this video. Thanks for watching. I'll see you next time.